Okay, let's quickly run through complex numbers. I will tell you that everything you learn in this video is enough to make you pass. However, unfortunately, you're gonna have to, if you want to achieve a 5, a 6, or a 7, you are going to have to go practice exam style IB questions, either from past papers or question banks, maybe like something like in thinking, cognitive, or even some of the textbooks are pretty good. Okay, let's start. The first keynote that we need to know, so let's figure out the keynotes here. So the first keynote that you need to know is that I is equal to -1. Essentially where that comes from is we can think about this as this common formula where we got I squared is equal to -1. Then if we root both sides, we can see that I is equal to the root of 1. And some people can argue it's plus -1, but it's besides the point. Okay, so let's use this principle real quickly to figure out that if I have I raised to the 3, well, I can break this up into I squared times I. And we know now we can substitute, since I squared is equal to -1, we can substitute -1 with I squared times I. And then we get that I raised to the 3rd is -I. Let's do one more example. Let's say we got I to the 4. Well, we know that I squared is -1, so we got -1 times -1. If I break this up into I squared times I squared, remember when we add, when we multiply exponents, they just add together. So it's going to be 2 plus 2, which is equal to I to the 4, which is the same as this particular question, yeah? And then we get 1. Okay, very, very easy. Let's move on to the next important point. So we're asked to find the square root of -16. Well, we know what the square root of 16 is, right? The square root of 16, since 16 is a perfect square, is 4. But now, what if I break this up into -1, the square root of -1 times the square root of 16? Well, since I is equal to the root of -1, I can then say I times the root of 16, which then simply gives me 4I. Okay? So what you're trying to do with negative roots is we could just take out, you can sort of think about it as factoring a -1. And when we factor the -1 or the root of -1, we substitute that with an I. Okay, but what if we're given an equation like this? Let's say we got x squared minus 6x plus 13 equals 0. Well, in this case, the first thing you need to notice is that we're going to use the quadratic formula. Depending on where the question's asked, if the question's asked in quadratics, they might make it a little bit easier, but since it's under complex numbers, the likelihood of using the quadratic formula is extremely high. So what can we do? Well, we can identify A, B, and C by just looking at the coefficients. So we got ax squared plus bx plus c. So let's go plug it in. So we got x12 is equal to -b plus minus the square root of b squared minus 4ac over 2a. Let's plug in what we know. Well, we know -6 plus minus the square root of b squared. So that's going to be -6 squared, which is 36, minus 4ac over 2a, which is 1. Well, that gives me 6 plus minus the root of, what's that? 4, what's that? 4, 40, 12, 52. 52 minus 36 is -16 over 2. Okay, but earlier we learned that we can use -1, the root of -1 times the root of 16, which is 4i. So I can now just substitute -16 with 4i over 2. And then we can simplify right through by 2 by factorizing a 2. So we got 3 plus minus 2i over 2. Cancel these two out. My final answer for the two roots will be 3 plus 2i. So essentially all you got to do in these particular problems is you just plug in a, b, and c in the quadratic formula. That's literally it. I mean, I don't think you can mess up from that point onwards, unless you forget how to solve a negative root. But just take out the I and use the root value, right? It's very, very, very straightforward. One thing that's important though is if we're given something like this, let's say we have z, I'll come back to z in a bit, but let's say we have 3 plus minus 2i. This is also, we can write this in the Cartesian form. Cartesian form, okay? Just something to keep in mind while we go through this video. Essentially, also another thing that you could do maybe in A levels is you're going to have to use the discriminant. So if the discriminant is less than 0, we'll most likely get these answers. So just a quick little revision. How do we find the discriminant? Well, our equation was minus 6x plus 13. By the way, if you're watching this video, I would assume that you have an understanding of quadratics. That would just be my assumption. If not, I would recommend you study quadratics first and then come back to complex numbers. So the discriminant, we can say that as x sub 1, 2 is equal to negative b plus minus the square root of the discriminant, or we can say b squared minus 4ac over 2a. So we're just looking at the following. We're just looking at b squared minus 4ac. So if I plug in these numbers, I can see it's going to be 36 minus 52. Oh wait, what is that? Let me plug it in so I can show. 6 squared minus 4a and then c. And then if I solve this, I get negative 16. And now we can clearly see we have some negative value there. So we're going to find complex roots. Okay, so if the discriminant is less than 0, we will find some complex roots. If the discriminant is equal to 1, we'll find one real root. And then if the discriminant, is equal to 0, we'll find one real root, one little connection. And then if the discriminant is greater than 0 or a positive value, we'll find two real roots. Okay, so that's the Cartesian form. But I'll just quickly rewrite it again. So the Cartesian form, depending on what curriculum you do, you can have in the United States, they use A. It's generally notated as Z is equal to A plus BI. However, some European curriculums like the IB use X plus YI. Essentially, it's the same thing, just different notations, right? So the first one, the first group, that shows me my real value of the equation. Secondly, I have, or we can notate it as R sub Z. The second part, the B and the Y, that is my imaginary part. Okay, so the BI, that's the imaginary component of my Cartesian form for complex numbers. Okay, let's continue. Okay, just something to keep in mind. Z is equal to I for this video, since it's IB related, I'm going to use Z plus XY, but just know that Z is equal to A plus BI is the exact same thing, just different notation. The example I always write here is, for examples, let's say I write hello and I write hello. Well, these are two different languages. It still essentially means the same thing. It's just written differently depending on the geographical location. Okay, so don't get confused if you now say, or if you see A plus BI or Z is equal to X plus YI. It really does not matter. Okay, now there's something we need to know. So again, let's focus on this Cartesian form. The reason this one is so important is because you need to know, you might have to switch between something that's known as a polar form, or Modulus-Argument Form. So getting familiar with the names is very, very important. Okay, so let's see. So again, we know that Z is equal to X plus IY. And just to be clear, is that X and Y is an element of all real numbers. They belong to the set of real numbers. Now, there's something that's known as a complex conjugate. conjugate. And the complex conjugate is very, very straightforward. Sometimes notated as a z with a star or a z bar. Again, depending on your curriculum. What this means, it's very straightforward. So if you see z star, all you have to do is flip the middle symbol. That's literally it. Flip the symbol. So if let's say z is equal to, let's do two examples, 3 plus I. Well, the conjugated form of 3 plus I, you literally just flip the symbol. It's that straightforward. Okay, let's do another example. Say we got z is equal to 7 plus 2i. Z star or z bar, depending on, again, which curriculum you study, is going to be z minus 2i. What about something like this, though? Well, now you might be confused. What about if it's 3i plus 2? I mean, you just do the exact same thing, right? We just flip the middle symbol from positive to negative, negative to positive. So z minus y, I. All right, let's go look at some examples. Conjugates should be hopefully engraved in your brain now. So let's say we got z is equal to 2 plus I, and let's say w is equal to 4 minus 3i. They ask us a couple of things. They ask us, we want to find a plus z plus w. We want to find z minus w. And we want to find z times w. Okay, very, very easy. So z plus w, we can just write it as 2 plus I is equal, or 2 plus I, 1 parentheses or brackets, plus 4 minus 3i. Just distribute the positive symbol, nothing changes. So it's going to be 2 plus I plus 4 minus 3i. And then we can see we add like terms, so that's going to be 6 minus 2i. Very, very easy. Okay, very simple. Don't let anyone tell you complex numbers is tough. Really, I don't believe it's very complicated. It's I'll try and make it as easy as possible. So let's say we got z minus w. Again, very, very straightforward. Plus I, basic. You learned this in grade 4. We just distribute the negative symbol. Every single symbol on the inside flips around. So that's going to be minus 4 plus 2 negatives makes a positive, plus 3i. So we have, what's that? Negative 2 plus 4i. Now what about multiplication, though? Multiplication's a little bit tricky. This is where it will be a bit tricky. So we got 2 plus I, 4 minus 3i. In this case, we just use distribution, even distribution, or we can use, maybe you might be familiar with the FOIL method. First out is in as last. Depending, again, the Americans in the United States, they use this method quite often. I just like to distribute, so everything in the left needs to multiply with everything in the right. So we got 2 times 4, which is 8. 2 times negative 3i is negative 6i. And we got plus 4i. And now notice the following. Notice that it's going to be I, or 3 times I squared. Okay, here we go. Look at that. Look at that. Now we know. So we learned earlier, since I squared is equal to negative 1, we substitute. I know I could have added those together, but just going to do it the long way. We substitute. Look at that. That's going to be plus 3. That becomes plus 3. So now we have 11 minus 2i. And there you go. Very, very easy. Okay, let's look at a very, very important key point. One important key point is that if z is equal to x plus yi, then z times its conjugated form is always going to be x squared plus y squared. Okay, so a little cheat code. For instance, if you're trying to quickly finish off work, you can just remember that key point. So let's look at an example. Let's say given that z is equal, again, remember Cartesian form. I'd say 2 plus 4i. Now I just want to prove that this key note that I showed you is true. So if that's the case, well, we can clearly see if we have x squared, y squared, we see that this is a number with no imaginary or no I. Okay, so the goal of using the conjugate is essentially to get rid of the I. So let's say z times z star is going to be 2 plus 4i. Multiply 2 again, just flip the symbol. Very, very easy, very straightforward. 2 times 2 is 4. 2 times that minus 8i plus 8i. And then we got minus minus 16i squared. And again, since I squared is equal to negative 1, we substitute it in. Plus, so that will be plus 16, which is then equal to 20. But let's look at this quickly in a different perspective though. So let's say I just took the following without even solving it. I know my final answer is supposed to be 20. So what if I just used my formula? So what if I said that x squared plus y squared will be equal to z times z star? And I could just essentially say that z times z star is going to be 2 squared plus 4 squared. That gives me what? 4 plus 16, which is also equal to 20. So we can clearly see this works. Now this is a very, very important concept to understand, especially if it comes to dividing complex numbers. Speaking about dividing complex numbers, let's check it out. So let's say I got 4 plus 2i, and w is equal to 2 minus 3i. Okay, let's say I wanted to find, let's say I want to find z divided by w. Essentially, I will substitute z and substitute w. Now here's the case. You see, we want it in the form, let's say z is equal to x plus yi, or it should be inclusive, bi. I want it in that form, in the Cartesian form at least, with no fractions. So what I can do essentially in this case is I can multiply the bottom side with the conjugate. Okay? So again, we think about this division as a, or this line as a mirror sign. So what I do at the top, I do at the bottom. So from my earlier proof, I know that I can just take this number squared plus this number squared. So that's very simple. So let's say we got 2 squared plus 3 squared. And then at the top, we're going to get 8 plus 12i plus 4i plus 6i squared. And then we get, what's that? 6i squared, that becomes minus 6. So that's 2 plus 16i over 4 plus 9, which is 13. Now I can simplify this if I really wanted to. I can say 2 over 13 plus 16 over 13i. And there we go. We got it in the form x plus yi. Although these are fractions, it's okay. Doesn't really matter. Okay. Let's look at another problem. What about if they ask you to find something maybe like this: 2z plus, let's say 2z plus 3z star is equal to, let's say, 2 minus 2i. Let's use this example for, let's use this case for an example. Now we know that, what do we know? Firstly, we know that z is equal to x plus yi, and we know that the conjugated form is y minus I. Now I can use this information to substitute it into my problem. So I can then say 2 times x plus yi plus 3 times, what's that? 3 times what? The conjugated form yi is equal to 2i. Now we just distribute inside here. We got 2x plus 2yi plus 3x minus 3yi. 3yi is equal to 2 minus 2i. Add the like terms. We got 5x minus, what's that? 5x minus what? Minus yi is equal to 2 minus 2i. Now we're left with this particular problem. Now essentially in this case what you could do is we're going to use something very, very different. We're actually going to set the real parts equal, and we're going to set the imaginary parts equal. What that means is I'm going to group certain parts. So I will group this 5x is equal to 2, and I will also group negative y is equal to negative 2. Now there's a particular reason we do this, is so we can find our final equation in the Cartesian form. So let me show you. So we can say the real part is going to be equal to 5x is equal to the 2. And if I solve for x, I get x is equal to 2 over 5. And then we can also say, well, the imaginary part is equal to negative y is equal to negative 2. So we see y is 2. So that means if x is 5 over 2, I can then say, in this particular case, z is going to be, the real part is 2 over 5 plus the imaginary part was 2, and I just add my I back into the equation, and there's your final answer. So the point of this question is, number one, substitute our z equation into the problem. If they ask you to substitute the conjugate, you do that too. You solve it, you get the left-hand side and the right-hand side. Leave the right-hand side. Solve the left-hand side. Try to create the left-hand side so it has one imaginary part and one real part. Then, if you have the left-hand side, you can set it equal to the right-hand side in terms of the real part and the imaginary part. Okay. What about a complex plane? Complex plane. What about if somebody asks us to plot? Let's say they ask us to plot the following. Let's say they ask us to plot 2 plus 2i. This is called a complex plane or Argon diagram. So it goes by two names. As you guys can see, so there's a couple of names here. Diagram. So we have a Argon diagram or a complex plane, and what we need to know about the following, it works like a two-dimensional plane, or I mean it is, but we have the real axis and we have the imaginary axis. Now this is very easy. Listen, it's super easy. If they ask you to plot these points, I don't think you can mess it up. Or maybe you could, maybe. Okay. So how do we do this? Well, let's say we need to plot the following. Let's say we need to plot z, we need to plot minus z, and maybe we need to plot the conjugated form. So first things first, we know that z is going to be 2 plus 2i. A minus z just means I'm going to multiply all of this with a minus. So that's minus 2 minus 2i. And the conjugated form, I know I just flipped the middle symbol, 2i. So on your complex plane, you just go look. The real part is 2 over there. Let me do it in red. The real part is here, 2. And then the imaginary part is also 2. So you just connect them. And there we go. There we go. Make a nice little dot. And we call that z. For the negative z, we just go -2 is there, -2, make a nice little point. We got z. The conjugated form, however, is +2, and we go down to -2, z star. And essentially, that's how you plot it. Very, very easy. Okay? Very easy. Okay. Now we're going to go to something that's a little bit more complicated. The easy stuff is done now. We're going to go something that's known as the Modulus-Argument Modulus-Argument Form. And I'm going to try to attempt to explain this firstly before we get to just simply the formula. Okay, I got some diagram. Let's say I got the following. Let's say I got z is equal to x plus yi. Okay, so we know this is my real axis. We know this is my imaginary axis. So let's draw some line. Okay, draw some line. Let's bring it down with a y, because obviously that's my y. And let's bring this one down with my x. But if anyone is doing the American curriculum, let's just do x is equal to a and then y is equal to b, right? I'll just write both of them down here, because I know sometimes they are a bit confusing. Okay. So let's call this r. And inside here, we obviously have some angle. We're going to call that angle theta. In this particular case, there's two things you need to know. You need to know that r is equal to the modulus. You can kind of just think about it as, in terms of Pythagoras, you can think about it as the hypotenuse. I mean, I'm saying you can think about it as the hypotenuse, right? Or you can think about it as a radius for a circle. A couple of ways you can think about it. Or you can think about it as a magnitude, right? The size of something. It also has a notation z with these absolute symbols. So r is the modulus. Okay. Theta, or theta, however you want to pronounce it, is known as the argument. Or you can literally just think about it as an angle. This also has the name, the argument of z. So those are the very important concepts we need to know. Okay. Now, if I look at this in terms of a triangle, I know that this is x, this is y, and this is r. If I wanted to find r, we know from grade 9 we can simply use Pythagoras' theorem. So it's x squared plus y squared, right? Pythagoras' theorem. Or we can say that r, which is equal to z, which is in for the Americans, a plus b squared, or a squared plus b squared. That's how we find the modulus. Now, provided that theta is not given, how can we find theta? Well, there's a very easy formula. We can say theta is equal to y over x, or b over a. And then to find theta, we just use the inverse of y over x. That's how you find theta. It's very simple. Those are our key two formulas. It's that r is equal to x squared plus y squared, the root of that. And then we got tan of theta is equal to y over x. Okay. Now, here comes the tricky part. But once you see it, hopefully you get it. So we got y here, we got x here. Theta. And then r. So essentially, we can also, first things first, let me just make this very clear, that the polar argument form also goes by a different name. This name is the polar form. So we can go by that, or we can say modulus argument form, doesn't really matter. But let's see, what if I wanted to find x though? Well, x I can find as, I can say the sine of theta is equal to the opposite, y over r. So then I can then say, well, if I cross multiply this r, I can say that r is equal to sine theta, which is y. Okay. What about if I use cosine of theta though? Well, cosine of theta is my adjacent over my hypotenuse. So I get x over r. So we can then say that r times cosine theta is equal to x. Okay. So I hope you guys are following. So if we then say z is equal to x plus yi, I can then substitute x because I know x is equal to r times cosine. I can substitute x with r cosine theta plus, and I know that y is equal to r sine theta. So it's going to be r sine theta I, which is z. I mean, I guess I could put the I in the front. Wait, let me put that I in the front so I don't make it confusing. I r sine theta. And then what about if I just factor out the r? So I can then say r cosine theta plus I sine theta. And that right here is the polar form. That's how you get it. It's just using trigonometrical ratios to substitute. I mean, it's just a direct substitution. That's literally it. Nothing more to it, to be honest. I mean, I'm explaining mathematics very informally, okay? But now I also want to show you a cis form. Now we can actually also write this as z is equal to r cis theta. So that's the two ways we can write it. I mean, there's another one, but we'll get to that in a little bit. So let's do one example. They ask us to write, let's say let's say z is equal, so again, we're currently in the Cartesian form, 1 minus I. In the polar form, okay, so what do we know? Well, we know that x in this case is equal to 1, and we know that y is equal to -1. So this is now very, very easy. What we can now do is we can easily find the modulus. So let's find the modulus r, or you can write z. And we know that this is the square root of x squared plus y squared. So that's going to be 1 plus -1 squared. So the modulus is -2. For this, you already get a point. Very, very easy. Very easy. Secondly, we're going to use the tan of theta is equal to -1 over 1, because we know it's y over 1. And -1 is, if we go look at this, if we go plot these points, it's going to be 1 minus 1. So it's somewhere over there. So we know that in this case, it has to be between 360 and 270. My advice would actually be always to plot the points, just to make sure that your angle is in the correct, or you're in the correct quadrant. You're working in the correct quadrant. Okay? So in this case, we can say, I mean, or you can type it on a calculator, but this is generally a paper 1 question, so maybe you don't have a calculator. Tan minus 1 over 1. We know tan 1 from this triangle, 1 root 2. We know tan 1 will be 45. So we know it's 45. But in this case, we can see a minus there. So I'm just going to say theta tan 1, positive 1, is equal to pi over 4, or 45. And then, since I know it's in the quadrant 2, all I'm going to do is say theta is equal to 2 pi minus pi over 4, because I'm trying to get into this quadrant right here. And that is 877 pi over 4. Okay, so now we know. We know that r is equal to the root of 2. We know that theta is equal to 7 pi over 4. So therefore, we can then write it as root 2 times cosine 7 pi over 4 plus I sine 7 pi over 4. Oh, I'm out of paper. Oh man. It. Okay. Give me 1 second. Just want to quickly erase. Okay. So now let's talk about the next concept then. What about if they ask us in the polar argument form to take it to the Cartesian form? Oh man, this is not good. This is very ineffective. I'll try write a little bit smaller. I really don't want to be clearing stuff all the time. Okay, I'm going to use this page effectively, starting right now. Right here. Okay, so they say complex number. Let's think of an example. Let's say we have a modulus of 4 and an argument z of pi over 6. They ask us to write this, so write in Cartesian form, Cartesian form. Okay, step 1, what do? We plug it in. We know that it's going to be 4 because the modulus position is here. Maybe I could just write the ghost formula quick. It's the ghost formula, so we can know what I'm doing. So we got cosine pi over 6 plus I sine pi over 6. Now listen, this is super easy. Listen, very, very easy. Just solve this one and solve that one. So what exactly is cosine pi over 6? What's that? 180 divided by 6 is what? That's 30, right? So we got cosine 30. What's that? That's root 2 over 3, isn't it? I think so. Plus I, if it's root 3 over 2, this one then has to be 1 over 2. It has to. Because they're opposites of one another, right? So you can shuffle between these two. If sine is that one, then cosine has to be that one. If cosine is that one, then sine has to be that one. Okay. So now, since we got these values, we could just distribute the 4 in. Very, very easy. Very simple. Okay, basics. Simplify, we get 2 root 3 plus I. There we go. Very, very easy. One and done. Boom. Now you can just practice a whole bunch of these questions as they come along. But now, what about the following though? Is another key little point we need to know. So a keynote. What exactly is this keynote? Well, if we have z is equal to r cis of theta, we know that the conjugated form is actually simply going to be r cis of a minus theta. Okay, so let's look at one example. So let's say we want to find z is equal to cosine pi over 5 minus I sine pi over 5 in cis form, cis theta. What we can then do is we can say that z is equal to cosine pi over 5 minus I sine pi over 5. And then we can rewrite this as cosine pi over 5 plus I sine minus pi over 5. And then since we use the keynote from up top, we can then say cosine negative pi over 5 plus I sine negative pi over 5. Since we need the same angle, we need the same theta in both left and right. And then we can then say, or both the same theta in sine and cosine. Then we can then say cis minus pi over 5. I mean, essentially what I could have just done is I could have just flipped the, or I could have just written it from the start. I just wanted to show the keynote anyway. Okay, very, very good, everyone. Wow, are you following? Okay, we're going into dangerous territory next. Danger. Okay, hope everyone's ready. Couple of keynotes we need to know. My advice would be for you to understand that arguments works as logs. So what does that mean? I mean, it works as logs. Okay, so a couple of things we need to know is that when we say the modulus of z and w, multiply the modulus of z times the modulus of w. It's very, very straightforward. The moduluses work the same. Same for division. So if we say the modulus of z divided by the modulus of w, we get the modulus of z divided by the modulus of w. Now in terms of arguments, however, if I multiply two arguments, this is going to be the argument of z plus the argument of w. This is why I say they act as logs, right? Act as logs. This is why I said it. Because we know in logs as well, when logs multiply, they add. When logs divide, they minus. The arguments work the exact same way. We can say the argument of z divided by the argument of w. Okay, very good, everyone. Oh, more goodness. Let's look at an example. Let's say we got z is equal to 2 cis pi over 2 plus, oh no, let's say we got pi over 2 and w is equal to, let's say, 4 cis pi over 6. Find zw and z divided by w. Okay, so first things first, what we got to do is, since it's a multiplication, I'm first going to find my modulus or my moduli. We know that it's going to be the modulus they just literally multiply. So we got 2 times 4, so that's 8. However, for my arguments, if I know that my argument zw, I know that they have to add when we subtract. So it's going to be pi over 2 plus pi over 6, which is 3, 4 pi over 6. And I can simplify that to 2 pi over 3. So then we can write my new form that zw is equal to my new modulus that I just calculated, cis, and my new theta that I just found, 2 pi over 3. Alright, please give me un momento. I just want to quickly clean over here. Otherwise, don't have any space to work. Un momento, per favore. Okay, let's go back to our investigation into complex numbers. Okay, next, we want to find z divided by w. Very easy, very straightforward. Hey, listen, super easy, super straightforward. Divided, we get 1 over 2. So we know my new r is going to be 1 over 2. And then for the arguments, so the argument of z divided by w is a very, very easy subtraction, very simple. Super easy, fam. So we got, what, 6 at the bottom. We got 3 pi minus pi. So that gives me a 2 pi over 6, which is pi over 3. So we can then just write again, very, very easy, where we have z divided by w is in fact my new modulus, 1 over 2 cis, and my new argumentos. Whew. Okay, what about something like this though? What about if they give us maybe, like, let's say 4 cosine 2 pi over 3 plus I sine 2 pi over 3 and w could potentially be something like 2 cosine, let's say maybe pi over 6 plus I sine pi over 6. Again, super easy. So they ask us to find z divided by w in Cartesian form, though. Oof. Wait, I'm spelling this thing wrong. Cartesian, Cartesian form. What about they ask us something like this, though? Oh, we know that first things first, I'm going to find z divided by w. They just act normally. So I'm going to say 4 divided by 2 is t. Now I need to find the argument of z divided by w. That's simply going to be a basic subtraction. Pi over 6. So we in fact get 3 pi over 2. 3 pi over 6, which is simply pi over 2, or 90 degrees to make it easy. Alright. Now I have to write it in my z divided by w. So z divided by w is going to be, I say 2 times my new cosine of my new argument plus I sine pi over 2. And now going back to basic trigonometry, we know that cosine 90 is 0. How do I know that? I just look at this number over here. We know that the coordinates there are 0, 1. The cosine at 90 is 0. The sine at 90, sine is always related to my y, cosine always related to my x. So we know that the cosine of 0 is, cosine of 90 is 0, and the sine of 90 is 1. So we can then say 0 plus 1i. So my final answer in Cartesian form is in fact 2 i's. We all have 2 i's, I hope. Alright, what about Leonard-Euler's form? So Euler form is very easy, or Euler. I like to say Euler though, but some people have corrected me, but I like Euler. I like Euler. So Euler's form or Euler's form is I pi theta, r to the I pi theta. And this is actually where the God equation comes from. For those of you who are interested, go check out that little equation. It's pretty cool. Okay, so again, it's literally so repetitive. It's just, whoa, why's my PC doing that? So the r is just a modulus again. Now we just place them on different locations, and the I is theta. So for instance, if I had, let's say I got the following. Let's say I got 2 cosine pi over 2 plus I sine pi over 2. If I had to write this in Euler's form, I can just say Euler. I could just say 2 e I pi over 2. Very easy, very straightforward. Again, easy as throwing a rock. Un momento. You can just skip the cleaning, by the way. Unless you want to watch the cleaning. It feels like cleaning a window, you know. I don't mind cleaning a window, actually. Alright, I got 2 fresh pages. Let's go. Okay, next. What are we going to do next? We're going to do another example using Euler's form. So let's say we're given the following. Let's say we're given z is equal to, let's do 12 e I 2 pi, or pi over 2. And let's say we're given 6. Let's say 6e I pi over 6. They ask us to find two things, zw and z divided by w. Okay, so let's do this is question A, question B. So for A, very, very easy. We just do the same thing. We say zw, find the modulus. By the way, we're just indicating there that we're finding the new modulus, huh? That's why we do it. So we know it's 12 times 6. Okay, this is going to be a very big one. What's that? 670, 72. That's 72. And then the argument of zw is pi over 2 plus my new modulus for zw and pi over 6. So that's going to be 4 pi, right? 4 pi over 6. I've got my new modulus and my new argument. Excuse me for my mispronunciation. So we can then say, well, zw. So zw is equal, in fact, to 72 e I 2 pi over 3. All right, all right. Let's do the next one, boy case. Here we go. Z divided by w. Very easy, straightforward. 12 divided by 6 is in fact 2. And then we go, the argument of z divided by w is pi over 2 minus pi over 6. So that's 2 pi over 6. Pi over 3. So we know that z divided by w is in fact my new modulus, which is ei pi over 3i. All right, very, very, very easy. Now we're going to do factorizing polynomials. Okay, so let's do some factorizing. Factorizing polynomials. So before we discuss the following, we discussed complex roots. What if you're given something like this, though? What if you're given x squared plus 6? Well, this one's very easy to factorize, right? Because we know the multiples of -4 and -2 gives me 8, and they also give me -6, which means x is equal to 4 and x is equal to 2. But now, what if we're given something like this? 6x plus 40. Okay, now in this particular case, it's very hard for me to figure out what is, we got -6. I don't know what the multiples of these are that could potentially give me -6. So once you're ever in a situation like this, step 1, chuck it into the quadratic equation. So we got -b plus minus the square root of b squared minus 4ac over 2a. Plug it in, -6 plus minus the square root of 36 minus 4ac. What's that? 4 times 40 times 1. That gives me -136 over 2. So we get 6 plus minus -100 over 2. And we learned earlier that I can just rewrite this as 10i over 2. And then we can finally simplify that my roots for this quadratic equation is in fact 3 plus minus 5i. All right. What's wrong, buddy? Okay, wow, ladies and gentlemen, that was indeed a tough one. But let's look at the following, though. What about if they say, maybe they give us something like this? What about if they say x cubed minus 5x squared plus 11x minus 15? And they give us one root. They given that x is equal to 3 is a root. How do we do something like this though? Okay, well, since we know that x equals 3 is indeed a root, okay, I can do the following. Now, just give me 1 second. I just want to quickly grab something, because I did not think this video is going to be this long. And to have a sip of water. 1 secondos. Right, just a 1 sip. Gotta stay hydrated, okay? You have to. Very important for the mathematical memories. Very important. Okay. So we're given the following problem. First thing we need to know, there's something that's known as the factor theorem. If you revised that already, good on you. If you haven't, it just tells us when a factor is given, that means if I plug 3 into the polynomial, I'm going to get 0. If I get 0, something is a factor. There we go. Good, good. Now, if I know that x is equal to 3, I can then say, well, x minus 3 is equal to 0. So this means I'm kind of reversing the factorizing process. Okay, so what do we know? Well, we know the following. We know that x minus 3 is some factor. Okay, so I can actually rewrite this. Now, keep in mind, this is a little technique. Your teacher might use a different technique. There's many, many different ways you can do this. You can either do this through something that's known as synthetic division. You can do this through something that's known as long division. Or you can do this through through inspection. Okay, inspection one is quite difficult. But essentially, we can do the following. Since x minus 3 is some factor. Sorry, I just need to erase it because it's going to be quite long. Since x minus 3 is some factor, we now know there's a quadratic that's left, because a linear times a quadratic is a cubic. So we know that ax squared plus bx plus c is left. We know that's left. Okay. Well, if that's the case, I'm going to expand this one now. So if I multiply, that's going to give me ax3 plus bx squared minus 3ax squared. Sorry, 3ax squared plus cx minus 3bx minus 3c. Now I can group the squares. I can group the single variables. So we know that ax3, and in this case, if we analyze this particular problem, 3ab squared, we know that the coefficient for x squared is going to be b minus 3a. So essentially, that's how I'm going to group it. Okay, I'm just grouping the coefficients, 3 minus ax, x squared, plus, in this case, it's going to be c minus 3b minus 3c. Okay, so now that I got this, I can now compare. Since I know my coefficient of x squared is b minus 3a, and I also know my coefficient of x squared is x2, I can now set them equal to one another. So you can compare coefficients, right? So that's essentially what I'm doing. I'm comparing coefficients. Coefficients. That's what I'm doing. So we can see that the coefficient of x cubed is 1. Okay, because there's only one, the a, and that a has to correspond with this one. So if a is 1, I can now compare x2. So I'm going to take that minus 5 is going to be equal to b minus 3, but we know a is 1. So therefore, b will be equal to negative 2 because we add 3 on both sides. So we got a, we got b. Now all I need is c. So I can either use this one. I can compare this to 11. Or I can simply compare the 3c to the 15. That one's going to be easier. So that's going to be x to the 0. So we get minus 15 is equal to minus 3c. So therefore c is equal to 5. Now since I got my coefficients of my quadratic, I know it's a little bit messy, it's a little bit challenging. We can then say, we can say that we know that x cubed, what was that equation? X cubed minus 5x squared minus 5x squared plus 11 plus 11x minus 5 is equal to x minus 3, and I just found all my coefficients. So it's going to be x squared minus 2x squared plus 5. And then I can use the quadratic equation. X1 sub 2 is equal to negative b plus minus the square root of b squared minus 4ac over 2a to solve this quadratic equation. And I can find all my roots. Okay, let's proceed. Now, what about if they give us complex roots though? So what I'll tell you is, if given complex roots, I'll just show you the technique. If given complex roots, we can use the following. We can use, this is also a keynote by the way, that x minus z conjugated form is equal to x squared minus 2 times the real value of z plus the modulus of z. Okay, so what exactly does this even mean? Okay, I'm given a polynomial x is equal to x cubed minus 4x squared plus x plus 26, and they say the root is equal to 3 minus 2i. How can we solve this? Very, very easy. Well, since a complex root is given, we're given a complex root, we know we can use this little formula right here. Okay? So essentially what this then means is, if I just plug in the values, I get then that since, we can say since I'm just going to write everything, minus 4x squared plus x plus 26 has a root 3 minus 2i. I can then say it can be x minus, I'm just going to plug it in there for reference, minus 3 plus 2i, and x minus the conjugated form 3 plus 2i. Okay, now I know this all still seems very, very confusing. But let's quickly just plug this into the formula so it makes sense. So since that is the case, I can say, therefore, if I plug this into the formula, I get that, since this is the case, we can say x minus 3 minus 2i, x minus 3 plus 2i is then going to be equal to x squared and 2 times the real number. So 2 times the real number is 6. So we get minus 2 times the real number of z, which is 6x, and then 3 squared plus 2 squared, which is 16. Is that? Wait, 9 plus 4. Whoa, that's 13 plus 13. So essentially that's all you do, you know. They give you the root. I'll explain it again. They give you the root. They give you 3 plus 2i. All you do is you look at this formula, minus 2 times the real number of z plus the modulus squared. All you do, very, very simple. You just put the x squared. And you say 2 times the real number. Well, the real number, if we go back to our example, where x is equal to the real, and then y is equal to the im, z of z. So you just take 2 times the real number. So you just take 2 times 3, which is 6x. And then we find the modulus. So the modulus is 3 squared plus 4 squared. No, plus 2 squared. That's 13. So it's just plus 13. Now we can say the following. Okay. So this one's going to be a little bit tricky, but try keep up. So we can then say that x3 minus 4x squared plus x plus 26 is equal to, well, we know this is the one of the roots. So we are missing an ax plus b, right? That's what we're missing. Because remember, from our previous example, we had the linear factor and we were missing the quadratic factor. This time we have the quadratic factor and we are missing the linear factor. So we plug this in there. Now we can solve this by inspection. So solve by inspection. Solve by inspection. And essentially how we do that is we see what exactly is missing in this particular case. So if I multiply a times ax, I get ax cubed. And we know that the quadratic of the cube is 1. So therefore we know that a is equal to 1. So we can see by inspection that a is equal to 1. For the final one, I see that b times 13, so b times 13 needs to be 26, right? If we just expand it normally, because if I multiply the two constants, that should give me 26. So b is then equal to 2. So b is equal to 2. So now since we found this, we can then say, in this particular case, we can then say, so x cubed minus 4x squared plus x plus 26 is in fact equal, if I substitute a and b back, we can say that x plus 2, and then we know that x squared minus 6x plus 13. So therefore we can say that the roots are x is then equal to 3 plus minus 2i. This is from my earlier answer. Oh, this is actually given to you in the problem. But remember, we used the because the root given was 3 plus 2i, but we also use the conjugated form. So we just indicate that. Using the conjugated form allowed me to get this quadratic equation. By the way, this technique just requires some practice. So we got that. Or we can then say, if I just solve this one, if I say x plus 2 is equal to 0, so therefore x is equal to minus 2, and then we get minus 2. Okay. Alright, let's end this video off with the Moivre's theorem. I know I'm pronouncing it wrong. The Moivre's. I don't really want to say that. The Moivre's theorem. So this theorem is very easy. I'm just actually going to abstain from pronouncing it. I'll just say this theorem. This theorem is super easy. Listen, it's super easy. If you have r cosine theta plus I sine theta, and we have this raised to the n, we can simply rewrite this as n raised to the r times cosine n times theta plus I sine n times theta. That's it. And we just got to remember that n is an element of integers. N is an element of integers. Okay? This is a very, very straightforward theorem. So they ask us to find something like this. Find 1 plus I raised to the 6 in, or let's make this 1 plus I raised to the 5 in Cartesian form. Actually, the 5 might become a little bit complicated. Let's use a hello? Hey! Why can I not? Ah! Oh, darn it, dang it, darn it. Okay. 1 second, please. 1 second, please. I just messed that up big time. I mean, I could cut this out, but I don't want to because it's going to require a bit of effort. So let's go again. The theorem. The moivres. The moi. It's like a French sound, you know, moi. The Moivre theorem. So we just know that it's r to the n times cosine n theta plus I sine n theta. And essentially how we do this is the question I gave a bit earlier was let's go I to the 6. Okay, first thing we want to find is we want to find the modulus in this case, because if I ever see something raised to the 6th power or something raised to any power, essentially the first thing I want to do is put it in polar form. Almost said polars, in polar form, and then from polar form I can apply the theorem, right? It makes perfect sense. So first things first, let's find the argument, the modulus, or let's just call this z, for example, z to the 6. So let me call that z to the 6. Okay. So let's find modulus. So it's 1 squared plus 1 squared, which is equal to the square root of 2. Okay, so we got my modulus. Cha-ching! Next, I can find my argument, or the argument of z, we know is tan theta is equal to 1 over 1. And as discussed earlier, theta will be pi over 4 since this is 45. Okay, now that we got those two things, let's just apply the Morph's theorem. So we know that it's going to be the square root of 2 times cosine pi over 4 plus I sine pi over 4. And we know all of this is raised to the 6th. So in this particular case, I know that this one, the r is going to be raised to the 6th. And this is just going to be multiplied with the 6th. So essentially what we got is this. We got to the 6 times cosine 6 times pi over 4 plus I sine pi over 4 times 6. Excuse me. I'm running out of space. What is that? That is... how can we solve this one? Well, we can just simply say, well, 2 raised to the 1/2 to the 6th. And that's going to be 6 over 2, which is 2 to the 3, which is 8. So I can say 8 times cosine 6 pi over 4 can be simplified to 3 pi over 2 plus I sine 3 pi over 2. And we know that is 270. So 270. Again, my cosine will be 0 at 270, as we discussed a little bit earlier. So it's going to be 0 minus 1. So that's going to be 8 times 0 plus, no, minus, because sine is minus 1 at 270, minus I. So my final answer is minus 8i. Okay, let me end it off with one final problem. It's my life. Dun, 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 dun. Okay, I'll end it off with something that's known as roots of unity, which is essentially where we're going to attempt to find z to the power of 5 is equal to 1. Very, very common question. So we can then say, let z is equal to r cis of theta. Now we're just going to find r and cis of theta. So in this particular case, we know that r, because z is now r cis of theta, so r cis of theta is going to be raised to the 5 should be equal to 1. So we can then say r to the 5, and then cis, applying the Moivre's theorem, is going to be 5 times theta is also then equal to 1. So in this particular case, since we only have a real component, we can then find the modulus. Well, the modulus is going to be, because essentially this is how it looks now. It looks z is equal to 1 plus 0i, right? So in this case, we know it's going to be 1 squared plus 0 squared, which is simply 1. So I can then say, well, r to the 5 is going to be equal to 1. And then if I say the tan of theta is 0 over 1, that's tan of theta is 0. And what's important to know here is that this occurs every 2 pi, right? So it's multiples of 2 pi. If we make a full rotation and try to plot it on some type of Argon diagram, right? So what we'll do next is we're going to say, so cis of theta, cis of 5 theta, is going to be equal to 0. And therefore, theta will then be, it's going to be 0. It'll be 2 pi, because we're making 5 rotations. 4 pi, 6 pi, and 8 pi. Oh, sorry, 8 pi. Why am I putting a theta? Then that means theta will be, obviously that's just going to stay 0, so it's going to be 0. 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5. So then we can say, then z will then be, it will be 1, right? Because it's r cis of theta. So it's either going to be 1, and it's going to be cis of 2 pi over 5, cis 4 pi over 5, cis of 6 pi over 5, and cis of 8 pi over 5. And if you really wanted to plot this on a diagram, you can just go find all these points on the diagram. And then the first point will be there. The second point will be somewhere inside here. The third point will be somewhere there. It will be somewhere here and somewhere there. We just connect it with some nice straight line. And then draw a little circle around. This requires a little bit of practice, but I'm running out of time, and I think this video is becoming extremely long. So I'll definitely do one where I do exam-style questions. That'll be the next video. This is just a concept overview if you're trying to pass. That's about it. All right. So if you pay attention to everything in this video, you could potentially pass. But there's one final thing. Oh man, let me do one final thing. In this case, so a keynote that we just need to take away from all of this is that the nth roots of unity the nth roots of unity are it's going to be 1, as we just saw a bit earlier, cis 2 pi over n, whatever that n is. Previously we had 5. We know that we had 5 in terms of my nth root. So remember, we had z raised to the 5. So in this particular case, if we had to rewrite it as cis of theta raised to the n, and then if we apply the Moivre's theorem or the Moivre's theorem, we got cis 5 pi. And so there we can clearly see that this n, excuse me, wait, I can't even back. We can clearly see that, hey, where'd it go? N of theta. So since this was 5, we can then say r to the 5 and then cis 5n. So in this case, n is clearly 5. That's why I placed 2 pi over 5. Okay? And then we just keep going. We make full rotations over n. So therefore, we can then say that cis is going to be cis parentheses 2n minus 1 theta over n, which is going to be eventually equal to 0. But this is only for when you have like a regular n-gon on the argon diagram. You want to use this. Okay. Is there anything I missed? I mean, I guess I missed trigonometrical identities. Maybe I could do one more example real quick. Yeah, let me do one more example. Okay, this is going to be a bit of a tough one, Let me do one more example. I feel like that's not good enough to pass. So if I do this, you could potentially pass. Let's use this example, plus 4i. Okay, so we know that z, we're going to let z is equal to 4, 3 plus... Ah! What am I doing, bro? Hey, yo, mandem, yeah? So we know that... Hey. Why is that thing not going? Okay, so we know that we're going to let z r cis theta. So again, we're going to have to unfortunately find we're going to have to find the modulus and theta. So if z is that, then we know that r cis of theta can be replaced with the z, and it's going to be 4 plus 4 plus 5, 4i. So that's going to be r to the 3 is equal to cis 3 theta, which is 4 root 3 plus 4i. Okay, so let me just find the modulus real quick. It's going to be 4, 3 plus 4, which is, it's going to be 4 root 3 to the square plus 4 squared. That is 16 times 3. What's 16 times 3? Oh man, I'm fried. My brain is fried. What's that? 18, 18, 48. 48, right? 48. 48 plus 16. What's that? 2, 5, 6, 64. Okay, so we can see it's a nice little 8. Okay, so we got that. And now let me find the argument as well. So the argument... the argument of 4 root 3 plus 4, that's simply going to be the tan of theta is going to be 4 over 4. Why is that one in a root? I'm so sorry. 4 root 3. These ones cancel out, so that becomes root 3 over 3 tan of theta. So that means tan, if I use the inverse, is pi over 6. Okay, cool. Cool. So now we know that r cubed is equal to the modulus of 8. So therefore r is then, if I cube root both sides, 3, 3, that's going to be 2. And then for theta, I know that 3 theta is equal to, in this case, it's going to be 3 cis theta is equal to cis pi over 6. And then I get that theta, 3 theta, if I divide both sides, is pi over 6. And then we can see that theta is going to be pi over 18 if I just divide both sides by 3. Okay, so therefore theta will be 3 theta will be pi over 6. So then theta will be pi over 18. Okay, that's the first step though. But now remember, we're doing the 2 pi rotations and I got 3 of them. So now if I add 2 pi for these ones, it's going to be the next rotation will then be, if this is 6, times the 2, that will be 13 pi over 6. And this one will then be 25 pi over 6 for my rotations. So I can then just copy them over 18. And this is going to be 25 pi over 18. And since this is the case, we know what the new modulus is. So we can then say z, because I need 3 of them, corresponding with this 3. We know that the new modulus is 2 cis pi over 18. We also know 2 cis 13 pi over 18. And we also know 2 cis 25 pi over 18. Okay, I think I'm gonna end the video there. That should be enough to get you to pass. The only thing I'm really still missing is solving Argon diagrams, and then trigonometrical identities and exam-styled questions. The trigonometrical identities, there's so many of them, so that will be a separate video. And then there'll also be an exam-styled question video. Okay, hope you learned something. Enjoy!